Hello students, welcome to the third tutorial on static equilibrium. In this video, we're looking at a uniform rod that is suspended horizontally as shown in the diagram. Then we're trying to use a few properties or a few concepts that we've learned to determine a few unknowns in the diagram. One, the things that we'll try to determine in this case, one is going to be the angle that the left end makes, the raw on the left end makes. And then apart from that, we also want to determine what FT1 is. So the tension FT1 is this side. So sorry, I didn't include those last time. So this is what FT1 is. So this is FT1. And then this side we have FT2. So sorry for not including them in the previous video. Okay, so I hope you guys try to just place them somewhere and then just try to work them out. Okay. Right. So since we know to say that this is equilibrium and working out questions to do with equilibrium, we're going to be adding forces for the most part. But then whenever we are doing this, we're going to be doing it in component form. So we're going to start right away by just resolving these forces. If I start with FT1, so what you guys have to notice is FT1 is in this direction. So this is the vector FT1. So what we're given is this angle, which is this side. So if I'm going to resolve FT1, what you guys should see is this face, since this is the angle we're working with, this is the 30, then this part here becomes, since it is opposite to that, this is FT1, meaning this part here is just FT1. So let me write it somewhere here. So this is FT1 and then sine 30. Hope you guys are getting a hang of how these concepts work. So let me use a different color for these forces. So this is going to be the component of FT1 that is in this direction. And this is going to be FT1 sine 30. The next part is to get the y component, which is this component going up. And then this, of course, it's going to be this face of this triangle. And what we see is it is adjacent to the angle here. So we're going to use cos. So this is going to end up as FT1 cos 30. So I hope you guys are able to get that. Let me just write this more clearly. So this comes out as FT1 cos 30. Nice. Okay. So the next part, we come to the other side. Again, the components, we have this vertical component. I hope you guys are getting the hang of it now. So again, this is adjacent to this. We're going to use cos. So this comes out as FT2 cos theta. And then this side, we're going to have the x component, which goes in this direction. Again, you can say we get it from the fact that it is the same as this side, which is here. Since if I was to draw that, we basically have this, the vertical one, and this we called it, this is FT2 in Y, which ends up as this. And then we have FT2 itself, which goes something like that. And then this side, this is where we have FT2 in X. But we know this will be the same as the face when it is down here. So that's why we're saying this face, since it's opposite when we relate it to the side which is that side. So, well, just in case you guys are struggling to see this, let me just do it properly for you guys here. So we're saying this is what we basically are looking at. Okay, so the angle we're given, or the angle we're working with, is this. So remember we said this is FT1 ft2 in y, and then this is ft2 in x. But then we're saying, all we want is to find the x component. So this ft2 in x is basically going to be the same as this one here. And this ft2 in y is the same as this one here. Remember, opposite sides of a rectangle are equal. So if we can find this, then we found that. So again, this is opposite, they are opposite. So you have sine theta is equal to the opposite ft2 in x over hypotenuse. The hypotenuse is ft2 itself. So over ft2. So this becomes ft2 in x is equals to ft2 sine theta. So this is how I get this. Then I substitute it for this side. So this is the same method I used to get ft2 in y. You can try it out and show that ft2 in y ends up as this. So from there, I can substitute it here. And what I have is ft2 in x becomes ft2 itself, but sine theta. Okay, so with that out of the way, the next thing that we have to look at is how can we work this one out? Now, the hints that I gave you guys had 3 steps. The first step had to work out the summation of the torques. The next step had to be the summation of the forces in the x, and lastly, the summation of the forces in the y. Now, how do you do this? You see, for a system in equilibrium, what we have to keep in mind is it is not rotating to the right, it is not rotating to the left. In other words, there is no clockwise rotation and there's no anti-clockwise rotation. So the torques are equal. So the clockwise moments and the anti-clockwise moments are equal. So now, just in case you've forgotten what torque is just the product of force times the distance. But there's only one catch to this. The force and the distance must be perpendicular. So they must be perpendicular. So I'm using this symbol to mean perpendicular. Okay. Now this makes it very important that if a force is given at an angle, then you have to get the component of it such that it ends up to be perpendicular. Like in our case, where we had a rod like this, and then we had tension which was acting at an angle like this. We can't use this force ft to ft1 and multiply it by some distance. No, we have to get the component which makes it perpendicular, which is a component like that. Okay. Now, one other key thing about torques and rotations that you guys have to keep in mind is a component of a force which passes through the pivot does not have any influence in terms of rotation. What do I mean? If you have the same rod, same one we're going the example, like this, and then you have T2, T1, this is T1, which has 2 components. Okay, so it has 2 components. One component is vertical, and one component is horizontal. Now, let's say we pick our pivot to be here. So this is our pivot. Now, what we're saying is, of these 2 forces, Ft2, T1 in X, and Ft1 in Y, this does not have any rotational effect since it is passing through the pivot. Why? Because in our definition of what torque is, I did specify that the 2 must be perpendicular. And if you look at the component, the x component, it is not perpendicular to the distance. The distance is from here, from the pivot to where the force is acting. So in this case, you see that the distance is in this direction and the force is in the same direction. So because of that, this force, this component of T1 has no rotational effect. But if you look at the y component on the other hand, it is perpendicular to the distance. So because of that, it will have a turning effect. So if we wanted to get the turning effect due to the y component of the Ft1, all we would have to do is, well, that turning effect, which is the torque, will be the distance from the pivot to where the force is applied. Let's call it L, since it's just the length of the rod in this case, multiplying the force itself. The force, we see that here, since it's the y component, it is perpendicular. So this is going to be times that component, Ft1 in y. So this is how we would get the torque of this force. Okay. Now this was just a brief reminder of torque and how to evaluate it. Now here, to really work out this question, now we're going to use this not just for one force, but for all of them. We're going to use this one at some point as well, but we just want to do it for all the forces now. Okay, so if we just resketch our rod, what we have is something like this. We want to identify all the forces that have a turning effect on this object. So now the first thing we did point out to say that the ones which are passing through the pivot do not have a turning effect. So the first step is, where is our pivot? The question does not specify where our pivot must be. We decide where the pivot must be. Now, the best thing that you guys can do is pick a pivot such that it eliminates some of the unknowns, as in it makes it easy for you to work out the question. So in this case, you guys can try to play out with this, position the pivot in different positions, but here you notice that it is easier to work out this if the pivot was way at the beginning of the road here. Why does this make the question easier? Because at this point, at this junction, at where the pivot is, there are two things that you don't know. One, the tension that is pulling this in this direction. Two, the angle it makes with the vertical or the horizontal. So it would be a little bit tricky for you to take this into account. You'd need more equations to work this one out. But on the other hand, if you had a way of eliminating these quantities momentarily, you would be able to easily find out what the missing components are. In some cases, it will be convenient to position the pivot at the center, but in this case, this point becomes the most suitable point to act as a pivot. Okay, now what happens? So since this is our pivot, any force passing through our pivot has no rotational effect. So remember, T1 or the tension one had two components, one in this direction, one in this direction. We see that this, if we extend it, it gets to pass through the pivot. So because of that, it has no rotational effect. If you don't want to say it passes through the pivot, you can argue that it is parallel to the pivot. It is not perpendicular, so it has no turning effect. So, but the y component on the other hand, the y component is perpendicular to the distance, so it remains. The next thing is the weight of the rod. So the rod itself has a weight, and the weight is a downward force. So let's just include this force and see the direction it goes in. Okay, so let's see. So the weight is somewhere on the central point of the beam. So, and it is going downwards. So we see that this weight, it is actually perpendicular to the distance. The distance is measured from the pivot to where the force is acting, and we see these are going to be perpendicular. So this is going to have a rotational effect. So this is Ft1 in y. Okay, so this will remain. Next, another object is positioned a quarter from the starting point here. So this object is somewhere here. Its weight goes down, and we see that this is going to be 400 newtons. And again, this force acts downwards while the distance is horizontal. Again, these two are perpendicular to each other. So this will have a rotational effect. And lastly, there's this force, T2, which has two components, one, this, and then the other, this. Now, notice that both forces pass through the pivot, and because of that, they don't have a turning effect. You can argue to say that this regardless, there's no distance here. There are many ways you can eliminate this. You can say since the distance here to where the force is 0, it means that there's no rotational effect. Or you can say they pass through the pivot, hence there's no rotational effect. I hope that's clear, you guys. So because of that, the force or the tension T2 has no rotational effect. We are only dealing with these three. So now, how does it look when we combine them all? So again, we're saying the sum of the torque must be equal to 0. So now let's take, since we don't know the length of this beam, let's say from the beginning of the beam, from the starting point to the far end of the beam, the total length, let's call it L. What it means is halfway becomes a distance L over 2, a quarter somewhere here to where the 400 Newton force is, the distance becomes L over 4, and the full length from here up to where FT1 is applied, the length becomes L. In other words, I'm taking this to be 0 and the far end to be L, the full length of the rod. I hope you guys are able to get that. So now, once you've got the torques to be equal to 0, next now, what does it mean? Let's start with the 400 Newton weight. This weight, remember I want to say the force, the weight, which is 400 times the distance to where it is. It is already perpendicular, so I don't have to resolve it. So the distance to where it is. So remember we did say here that this is a quarter from the starting point. So this is just going to be L over 4. So this is L over 4 plus, so this will give us the torque. So I can say this is the torque 1, or the torque due to this. So this gives us torque 1. So I can say this gives us torque 2. There are 3 forces, and this will give us torque 3. So there are 3 forces, so we're adding the torques, those 3 torques. So plus, now the next thing that you have to notice is the direction. It's up to you to choose which direction of the torques you want to be positive. Here, by doing this, I'm saying these two are pulling this down, so they're having some form of a clockwise rotation. So why am I saying clockwise? The point is here, this force is kind of trying to rotate this like this. This force as well is kind of trying to rotate this object like this. But look at this force here, T1. It is the only one trying to rotate the object the other side. So I'm going to take this to be positive rotations, and then I'll take this to be a negative rotation. So when it comes to torque 2, what I have is the weight itself. So the rod is given to have a weight of 120. So it's force times the distance. So the distance is half the full length. The full length is L, half of it now. So that's over 2. Remember, I'm saying let's take the length of the rod to be L, meaning the weight will act on the center, and on the center, the length must be half, the distance must be half the full length. Okay, now next part, now I'll have minus. Why am I saying minus? It's because now the torque I'm adding is in the opposite direction to the first two. So, but what is that force? That force is the y component of T1. So this now is multiplying the distance to where it is. What is the distance? In this case, it is the full length of the rod. So this is what gives us 0. Now, let's simplify. 4 can divide into 400. This remains as 100L plus 2 can divide into 60. This into 120, I mean. This remains as 60L minus, now what was FT1? We did have FT1 earlier. If we go back to our diagram, we found it already. FT1 in Y, it was FT1 cos 30. So if we go back, we're saying this is FT1 cos 30. FT1 cos 30, then this is times L, and this is what gives us 0. Now, here, the L, notice that it can cancel out throughout. It's there on each term and they are multiplying. So you can cancel out. So you can factor it out and then divide it both sides. So we remain with 100 plus 60 minus ft1 cos 30 is equals to 0. The ft1 cos 30 goes the other side. You can add this, you get 160 is equals to ft1 cos 30. So divide both sides by cos 30. You now have 160 cos 30 is equals to ft1. Then from here, when you simplify this, you should be able to find ft1 as 184.8 newtons. Okay, so this was step one, working with rotations and torques. So don't forget, it's the things that you have to do to get this. Torques, the product of force and the perpendicular distance. So if the forces are vectors, resolve them to get the components which, the components of the forces. And then only use the forces which are perpendicular to the distance because they're the only ones that give rotation. And then avoid the forces that pass through the center, not the center really. Avoid the forces that pass through the pivot because those will not have a rotational effect. Okay, so having done this, step two will now be to look at the forces, equating the forces. So it's equilibrium in terms of rotation and equilibrium in terms of the forces. So in terms of the forces, let's start with the forces in terms of the x. The forces in the x must be equal to 0. So if you go back to our diagram, there are two forces in the x. This force due to ft2 and the other force due to ft1. So the force, the x component of t1 is going to the right, so it's going to be positive. The x component of due to ft2 is going to the left, so it's going to be negative. So we already saw how to get those. So I won't take time writing those. I'll just bring them here. So ft2 is going to the left, it's negative. ft1 is to the right, so it's ft1 x minus ft2 the x. So remember ft2 is negative because it's going to the left. So next up I can bring in their formulas. So here we have ft1. So this is sine. The angle here is given, it's 30 minus ft2, and then this is sine theta. This is equal to 0. So one term can go to the other side. We now have ft1 sine 30 is equals to ft2 sine theta. It becomes positive and goes the other side. So I can just rewrite this now. So what I have is ft2 sine theta is equal to, we found what ft1 was. We had 184.8 newtons. So this is multiplying sine 30. Okay, so from here you can simplify. This is ft2 sine 30 is equal to, so this can divide and we get 92.4 newtons. So we hold on to this as our first equation, and then let's move on to the sum of the forces in the y-axis. So in the y-axis, if we go back to our diagram to see what forces we have. So in the y-axis, I think this already has, but don't forget, here we're not looking at the torques. So the pivot, we don't longer talk about the pivot, so don't worry about where the force is and so on. So in the y, we have four forces, ft2 going up, ft1 going up. And then you have two forces also going down. So the forces going up must be equal to the forces going down. Or we can just say ft1 going up, positive, this is in y, plus ft2 going up, positive, minus the weight of the rod going down, minus the mass, that weight, the 400 Newton weight going down. So it's also negative. This must be equal to 0. So from here, what we have, ft1, remember the formula for ft1 in y. So what we had there was ft1 cos 30 plus ft2 cos theta minus 120, the weight of the rod, minus 400 is equals to 0. So what we now have, we know what ft1 is, already found it. So we can substitute it here already. And then what we have is 184.8. This is cos 30 plus ft2 cos theta. This becomes minus 520 is equals to 0. So from here, this can move the other side, like term. So we remain with only this term on the left-hand side. This is now ft2 cos 30, cos theta, I mean. This is equal to the 520 becomes positive, but now minus 184.8, but now this is cos 30. Okay. Right. Now from here, there are various ways we can work this one out. So this becomes our equation 2. So you can say this is equation 2. So what I like doing here is I notice that the left-hand side of equation 2 and the left-hand side of equation 1, equation on the other side, they are trig functions. So I can divide equation 1 divided by equation 2. What I notice is I'm going to have the left-hand side as ft2 sine 30, this is sine theta, sorry, sine theta, from equation 1 divided by ft2, and then this now is cos theta from equation 2, and then the right-hand side is 92.4 from equation 1 over 520 minus 184.8 cos 30 from equation 2. So this and this cancels. We remain with tan theta is equal to 92.4 over 520 minus 184.8 cos 30. So from here, you get tan inverse of this. So this becomes theta is equals to tan inverse of this function, 92.4 over 520 minus 184.8 cos 30. And if you did that, you expect to get theta as 14.4 degrees. Once you've got this, you can get now equation 1. Remember what equation 1 was? So from equation 1, what we had was, so this is from equation 1. What we had was ft2 sine theta is equal to 184.8 sine 30. Actually, this was simplified already to become 92.4 ft2 sine 30. So from here, we already know what the theta is. We just want to find what ft2 is. So this becomes ft2 is equal to 92.4 over sine 14.4. So we evaluate this and we find ft2 as 372 newtons. Okay, so I hope you guys were able to follow. So the first step that we did was to include talk here. So talk, I think you guys need to spend a little bit of time to go through that. Let me know in the comment section if you have any trouble there, so that I find another question that I can upload that has that concept as well. Otherwise, this is how you do that. The first step, we use the talks to find a missing term. So we picked the best. We had to find the suitable position for the pivot when evaluating the talk, so that we eliminate some of the unknowns to make the question a bit easier to work out. If you pick a wrong position for the pivot, the question might become a little bit tricky for you to work out. Okay, so the next thing that we did then was to equate the forces since the system was in equilibrium. Okay, so I hope you guys found that a little bit easy to work out. In our next video, we're going to try out this question. So this now is for a ladder that is leaning against the wall. So I'll leave you guys with this for now. I'll ask you guys to try it out. I hope you will manage. If you have any trouble, you can wait for the next upload. Otherwise, we'll see you in the next video. This was your tutor.